So we want to know whether this system, this family of vectors is linearly independent. So we just have to write the definition of linear independence. So can we find lambda different from 0? Lambda k is different from 0 for k equals to p plus 1 up to n, such that lambda p plus 1 e p plus 1 f, sorry, f of e p plus 1 plus lambda n f of en is equal to 0. If so, then it's not linearly independent, and if we only have the case when lambda k are equal to 0, then we have linear independence. So let's rewrite these last equalities. What does it mean? I'm going to use the linearity of f. It makes f of lambda p plus 1 e p plus 1 plus up to lambda n en is equal to 0. What does it mean? It means that this element of E, lambda p plus 1 e p plus 1 plus lambda n e n belongs to the kernel of f. Okay, because f applied to this element is equal to 0. But we had built these vectors ep plus 1 en as the ones we needed in order to complete the e1 up to ep, those ones. Okay, we already had these as a basis of the kernel of f, and the next ones from ep plus 1 up to n, well, they were what we needed in order to complete that basis from the kernel of f. So by constructions, ep plus 1 up to en don't belong to the kernel of f, but what it means is that I must have that this linear combination belongs to the kernel of f, so the only way to do this is to have that lambda p plus 1 up to lambda n is equal to 0. So that this linear combination is actually equal to the 0 of e plus lambda n en is equal to the 0 of e, which belongs to the kernel of f. Okay, and that's it. So we have this system is linearly independent. And this is, and then in conclusion, we have that the dimension of the image of f is equal to, well, the number of linearly independent vectors. So we have n minus p, which is actually equal to the dimension, n is the dimension of e, and p is the dimension of the kernel of f, so that usually it's written as the rank nullity theorem. The dimension of e is equal to the dimension of the kernel of f plus the dimension of the image of f.